For anyone who has ever had to memorize a daunting list of equations for a finance exam, the one for the present value of a perpetuity must seem like a welcome oasis of simplicity. With so much else on your plate, you were probably relieved to be able to quickly register the C divided by R formula and then move on. But there is a surprisingly rich and interesting mathematics behind one of the simplest equations in finance. So in this video, we're going to take a look at the background to the perpetuity equation. We will use the example of a perpetuity of $1 per year with a required rate of return of 10% per year. To start looking at this question, we set up the timeline and we then calculate the present value of the first few $1 receipts. The first one, 1 year from now, has a present value of $1 divided by 1 plus the required rate, which in this case is 10%, for a present value of 90.9 cents. In 2 years' time, we receive the second dollar in the perpetual stream. This time, the present value is 1 divided by 1 plus r squared, for a present value of 82.6 cents. The present value of the third dollar is calculated as 1.10 cubed for about 75 cents. And so on. We could keep going, adding up ever smaller present values as we go further down the timeline into the future to infinity and beyond. Each subsequent dollar is worth less than the previous one when brought back to T0, which is today's value. This raises an interesting question. How can we possibly add up an infinite number of these decreasing values? Is there any point in doing so? The sum seems to be getting larger, but that increase in each case is in smaller and smaller increments each time. Is there a finite answer? In mathematics, we ask, does this solution converge? And it turns out that indeed there is convergence. The present value of this infinite stream of annual $1 payments turns out to have an elegantly simple formula. It is just 1 divided by r, where r is our required rate of return. With the 10% rate that we are using in this example, that means that this perpetuity is worth, and the point here is it is not worth approximately $10. It is in fact worth exactly $10. In the next part of this video, we'll take a look at why this surprisingly and perhaps suspiciously simple formula does indeed work using the mathematics of an infinite geometric series. So now let's see why the present value of our single dollar perpetuity equals 1 divided by r. We can write this mathematically as an infinite sum where each term represents the present value of one of those single dollar future payments. That's the equation in yellow. That equation might look intimidating, but it is actually a special type of series called an infinite geometric series. What makes this a geometric series? Let's write out the first few terms in white and think about it in a little bit more detail. We notice, having done so, that we have a first term and that after the first term, each subsequent term is found by multiplying the previous term by a constant called the common ratio. The series is the sum of all the terms in this particular sequence, and there is an equation for that. That sum is the first term divided by 1 minus the common ratio. In our perpetuity, the first term is 1 divided by 1 plus r. Interestingly, in this particular example, and this is something that is most certainly not a generalization, but here we have our common ratio, which also happens to be exactly the same as the first term, which is 1 divided by 1 plus r. When we substitute these values into our equation for the geometric series and work through the algebra, we see that something very interesting happens. The denominator simplifies to r divided by 1 plus r, and when we do just one more step, we see that everything neatly cancels out to leave us with just 1 divided by r. Going back to our example with a 10% required return and a $1 periodic perpetuity, we see confirmation that the value of that perpetuity is 1 divided by 0.1 or $10 exactly. If you're interested in where that geometric series equation comes from, let's let the sum equal s, the first term be a, and the common ratio be k. Then we can write out s equals a plus ak squared, and so on up to infinity. Next, we can multiply both sides of that equation by k, ending up with ks on the left-hand side and the terms that you see on the screen on the right. We deduct the one from the other, and in so doing, we see that every single term after the initial a cancels out, leaving us with s minus ks equals a, and with just a little bit more algebra, we see confirmation that our sum is the first term divided by 1 minus the common ratio. Let's visualize what we've just seen by graphing the present values of each of those single dollar future payments. We'll put time on the horizontal axis and present value on the vertical. For each future dollar payment, we can represent its present value as a vertical bar. The first payment 1 year from now has the highest present value. The second payment's present value is lower, and the third is lower still. Each bar represents the present value equation we used earlier. For the first payment, it's 1 divided by 1 plus r. For the second, it's 1 divided by 1 plus r squared, and so on and so on. As we extend further into the future down our timeline, those bars get progressively shorter, but they never quite reach zero. They continue infinitely into the future, getting smaller and smaller. And that is the remarkable thing about the mathematics that we did in the previous part of this video. When we add up all those bars, going out to infinity, we get that elegant result of 1 divided by r. Each of those bars represent one term in our infinite geometric series, but we have successfully shown that we can combine every single one of those infinite number of terms in that series into that single result. This visualization sets us up for an interesting question, which will be the last part of this video. What will happen if we receive those payments more and more frequently? Instead of annually, what if we receive them monthly, daily, or even continuously? So instead of discrete bars, we might expect in the limit to see a smooth curve, and that's what we are going to look at next. Instead of those individual separate payments, what we have now is a continuous flow of cash happening at every possible moment in time. In the example which we used to start this video, we were receiving $1 at a single moment in time at the end of each year. In this analysis, we would be receiving a continuous flow of cash, which doesn't mean at all an infinitely sized flow of cash. It just means that the $1 per year arrives continuously like water flowing from a hose pipe. But it is in total $1 per year that flows from that metaphorical hose pipe of cash. So what we have here is, instead of those separate individual bars, we have a smooth curve sloping down and to the right. In mathematics, you might hear that referred to as an exponential decay curve, but never mind that. For our purposes, the curve shows how the present value of our continual flow of cash decreases over time. At any point in time t, the present value is given by e raised to the exponent of negative rt. This is the continuous time equivalent of our previous formula for discrete cash flows, 1 divided by 1 plus r to the t. And what is really interesting about this is that the present value of that continual flow of cash arriving in our example at the rate of $1 per year, but arriving continuously, is represented by the area under the curve. And we can solve for that particular area using a little bit of calculus. It is the integral of e to the minus rt from 0 to infinity with respect to t. That integral resolves to 1 divided by 1 minus r times e to the minus rt, and we evaluate that from 0 to infinity. As t approaches infinity, the e to the minus rt term approaches 0. When t is 0, the e to the minus rt term resolves to 1. And that means that we have a situation in which the evaluation of that definite integral is 0 minus 1 divided by minus r, which gives us exactly the same result as before, 1 divided by r. And that is it. This video has covered a very niche topic, so if you've watched to this point, thank you very much. I really appreciate it, and I believe that you are probably going to turn out to be one of a very select few, but that's awesome. I hope you found this interesting, and I will see you in the next Finance Fundamentals video.